Okay, welcome. This is question 1 and 2 on the exam style questions, page 90 in the exercise book. First question, 1A, asks you to define field strength at a point in a field, an electric field, and you want to basically say something along the lines of the force per unit charge acting on a small positive test charge. We need the words positive to be in there, definitely. I've not written the word positive, but you know what I mean. This positive needs to be in there, force per unit charge needs to be in there, and after what we've discussed last lesson, I think that you should actually qualify that it's acting on a test charge, because that's in the syllabus. So a small test charge, remember, test charge is something that doesn't affect the actual field it's in. So you wouldn't say it's the force acting on a coulomb of charge, you'd say it's on a force per unit charge acting on a small positive test charge. Of course, it's a vector quantity because a field shows the direction of a force, and force has direction. Okay, part B. We have this situation of 4 nanocoulomb charge and an 8 nanocoulomb charge, positive and negative, separated by 80 millimeters. And you want to calculate the magnitude of the force exerted on the 4 Newton charge by the 8 Newton charge. Obviously, they're both going to exert the same force on each other, but in opposite directions. And so we just plug in Coulomb's law. Obviously 1 over 4 pi e naught, if you don't know that, has the value of 9 times 10 to the 9. So when you shove in your values, it comes out to 4.5 times 10 to the 5 newtons. Okay. Now that will have a negative sign in it. It doesn't matter if you have the negative in there or not, because it's only asking for the magnitude of it. Question B, part 2, asks us to determine the distance from the 4 nanocoulomb charge to the point along the straight line between the charges where the potential is 0. So if we set this up, potential due to Q1 plus the potential due to Q2 is 0. This is somewhere along here. Logically, it's going to be closer to the smaller charge and further from the big charge, so roughly around here somewhere, who knows. And we can therefore say V of Q1 is equal to minus V of Q2, and then basically we put in our equation for electrical potential. Again, we have the 1 over 4 pi e naught on both sides, so we can get rid of that and multiply across, and we end up coming out with R being 0.027 meters. Okay, now so if you see here, what I've done is I've said R, it would be this distance here, and this side would be 80 minus R. Okay, when you do that, shove in your values, it comes out to 0.027 meters, which is 27 millimeters from Q1, which is this one here. Okay. All right. Question number 2. It asks you to show that the force was given by mg tan 6.0. So you need to set up a little drawing like this. There's our string. The angle that it makes from the vertical is 6.0 degrees. Therefore, the tension runs along the string. Therefore, the vertical component of that tension will be given by 6, so T cos 6.0, and the horizontal component of this tension will be given by T sine 6.0. Now, the weight is obviously equal to the mass of the weight. So the weight is equal to the T cos 6.0, and the electric field, which is dispersing it from hanging vertically downwards, is equal to T sine 6.0. So you can set these two statements up here. T sine 6.0 is equal to the electric field, the force due to the electric field, sorry, and T cos 6.0 is equal to the weight. Now, of course, if you divide one by the other, you end up with sine divided by cos, and you lose the tension, the value of the tension. So you end up with tan 6.0 is equal to Fe over mg, and multiply of course by mg. You get the statement that they wanted you to show. Which is of course electric force. The force due to the electric field is mg tan 6.0. Okay, B. wanted you to calculate the electric field strength between the plates. Now they tell you that the potential difference between the plates is 4,200 volts and the separation of the plates is 60 millimeters, so 60 times 10 to the minus 3. E equals V over D. That gives you 7.7 times 10 to the 4 newtons per coulomb, or volts per meter, whatever you want to put in. Okay, for part 2, it asks us to calculate the charge in the sphere. So we know from up here that this term basically gives us the force, and that the force, of course, is equal to the electric field times by the charge on the sphere itself. So basically, I put this in the wrong way around, but Q is going to be equal to mg tan 6.0 divided by E. And if you put in your values, it gives you the mass of the ball, which is 2.1 times 10 to the minus 4, times by gravity, times by tan 6.0, divided by the field strength we found up here. And that comes out to 3.1 nanocoulombs. Alright, so that is question 1 and 2.